Now, based on that model, we're going to try to answer the questions that we raised the other day. And these questions, if you remember, are whether we can generalize in the sense that the risk that we compute empirically based on the data set and a given hypothesis is actually representative of the true risk, which is what we care about if we're confronted and given unseen example. So in the grand scheme of things, our objective is to find a hypothesis, which I call H star, which is the one that minimizes over all the hypotheses in your set, the empirical risk. All right, so that procedure by which you select a model that seems pretty good given your data by minimizing the empirical risk is called empirical risk minimization, or ERM. We'll see that quite a bit in this course. Now, understanding how the true risk of H star compares to the empirical risk of H star that you can compute, that's a bit complicated to do that directly. So what we're going to do is we're going to make a detour, and we're going to start by asking a simpler question. And that simpler question is the following. If I give you a fixed hypothesis, which I call Hj, that belongs to the set calligraphic H, so it's a fixed model, how does the empirical risk of Hj, which you can compute, compare to the true risk of Hj, which you cannot compute because you don't know Px, you don't know Py given it? And it's a complicated question, but we're going to make a very simple and very fundamental observation. Remember that in our framework for supervised learning, we view the data set as a realization of a random variable. There's an underlying probability distribution, Px, associated to that. And similarly, y could be random variable. We're assuming that it's just a deterministic function of x here. There's no noise. But if you look at the empirical risk, r hat n of hj, by definition, as we said, it is 1 over n, the sum from I equal 1 to n of this indicator function. Now, if you look at that indicator function in the eyes, and you think about the feature vectors as random variables, which have a distribution px, these xi's here, what do we know about them? These xi's are id, and they're all distributed according to px. Now, hj is a model, it's fixed, so hj of xi is a function of the random variable xi. Now, the indicator function is also a function of the random variable xi, and yi here in my model is actually a deterministic function of xi because there's no noise in the label. And so as a result, you see that this indicator function here altogether, you can view them as by definition being a random variable, which I'm going to call zi. Okay, it's indexed by I because it depends on the random variable xi, and because it only depends on xi, because all the xi's are id according to px, we know that the di's are actually id too. And so the result here is that the empirical risk that we're after, that we evaluate for the model hj, turns out to be a normalized sum of id random variables. Okay, so far so good. So what? Well, the good news is that such quantities are quantities that are really well known in probabilities and statistics, and people know a lot about what to say about them. The other observation that we can make very briefly is that if you take the expected value of the empirical risk, so when I write an expectation like this, you should always ask yourself, what is the expectation over? Well, what is random in my definition of the empirical risk here? If you go back to the definition, what's random is the random variable xi. So the expected value here is over all the data set D, which is a random variable since its components, the feature vectors xi from I equal 1 to n, are indeed random variables. So we can take an expectation, and I'm claiming that if you take the expected value of the empirical risk, it is actually equal to the true risk of the model hj. So how do we check that? We write the definition. So we're taking the expected value of what? Of 1 over n, sum from I equal 1 to n, indicator function of hj of xi not equal to yi. Now, if you remember a little bit of probability, expectation is a linear operator, which is a fancy name for saying that you can flip the order of expectation with sums. Sometimes with integrals too, but you have to be a bit more careful. Here it's a sum, so I don't have to worry about it. And so I can write that as 1/n, the sum from I equal 1 to n, expected value of an indicator function, hj of xi not equal to yi. Okay? So again, we see an expectation of an indicator function. So let me look at the term inside that expectation here. If you remember, this is what I called zi just a few seconds earlier. This is zi. In principle, it depends on I. So how can I compute the expected value of this zi? Well, let's look at it in the i's. It's the expected value of zi, and it's the expected value, as I mentioned earlier, over the random variables xi and yi. These are the random quantities. I'm going to highlight them in red. Okay, these are the random quantities here, xi and yi. So I could write expected value over xi and yi. These are my random quantities. Now, if you write the definition, well, an expectation is the sum over all possible values that xi can take, a sum over all possible values that yi can take. But then you have to ask yourself, what is the distribution with which I generate xi and yi? Well, if you remember correctly, a key assumption I've made in that supervised learning framework is that all my xi's are generated iid according to the same distribution px. And I have py given x for the label, which is independent of I. And so the joint distribution that matters here is pxy of xi, yi. And then I have to apply the indicator function, hj of xi not equal to yi. So once you realize that, if you look at this expression in the i's, it's not too hard to see that the index I plays absolutely no role. The index I only shows up in xi and yi, but that's just my way of indexing the realization of the random variables. For all I care about, I could call that u and v. And if I do the correct substitution by a change of variable, there is no dependence on I. And so as a result, what I'm claiming is that this expectation, which seemingly depends on I, actually does not. And this is just the expectation over xy, where the distribution of x and y are the ones given in the model, of the indicator function of h of x not equal to y. And by definition, as we saw before, this is the probability that you're making a prediction error, h of x not equal to y, and that's by definition, because we're using a binary loss function, that's the definition of the risk. Okay, so that observation is true. The expected value of the empirical risk is the true risk. And perhaps the one step that I've went over a little bit quickly is I'm proving that the expectation of the term zi is a constant equal to r of h. So if you average it, it is indeed equal. So with all that at hand, we can actually put pieces of the puzzle together a little bit and make the following observation. If you ask the question, can you compute the probability that the empirical risk evaluated on your data set for model HJ exceeds the true risk of the model HJ by more than epsilon in absolute value? Okay, so mathematically, the probability that the absolute value of the difference between r hat n of hj and r of hj greater than epsilon, that probability is actually trying to make a statement about a deviation of a very, very specific random variable. So again, just to be clear, and I'll do that for that lecture to avoid any misunderstanding, what is random, what is not random here? The quantity that I'm boxing in red here, this is the random variable. Why? Because it depends on the data set, which is a random quantity according to my supervised learning model. R of hj, which is the true risk, as we discussed during the last lecture, is a constant. It's a number. And so if you look back at what we said about r hat n of hj, it is the sum of id random variables. R of hj is actually the expected value of that sum of id random variable. And so that probability is making a statement about the deviation of a normalized sum of id random variable from its mean. So that might sound a little bit obscure if you don't remember too much probability, but it's actually the kind of quantities that we study a lot in probability. They're known as tail inequalities, concentration inequalities, and they're statements about how far a sum of ID random variables deviate from their sample mean. And we know a lot about these things. An example of that you have seen, without me really saying it, is when we talked on the last lecture about flipping a coin. When I mentioned the weak law of large number, the weak law of large number is exactly a statement of that form, as we're going to see shortly. In terms of learning, what's going to happen is that through the analysis of probabilities of events of that form, we're going to be able to understand how that probability behaves as a function of two things. One, as a function of the number of samples n in your data set. Two, as a function of the cardinality of the hypothesis set H. And we'll see that there is a trade-off and an interplay between the two that is perhaps surprising, but leads to the very fundamental learning trade-off. So the good news is that we don't have to do too much work in this class. A lot of smart people have spent many, many years devoting their lives to studying concentration inequalities. I have a textbook in my office called Concentration Inequalities, which is probably as heavy as you can imagine, that developed the topic in a lot of details. The good news is that for us, we can take that textbook, take the content, and apply that to analyze the probability that we're after. So again, to wrap up, when I say can we learn, the first question that we're trying to answer is whether the empirical risk that we're computing on a specific model has anything to do with a true risk. And the answer is not going to be a yes or no answer. It's going to be a probabilistic answer. We're going to try to say, well, the probability that they're more than epsilon away from each other is no more than some quantity, and we're trying to understand how that quantity that bounds the probability behave.